All right, today we're going to crack open a biological mystery, one that gets to the bottom of a really frustrating and surprisingly common hearing problem.
So, have you ever been in a crowded room, a restaurant maybe, and found it almost impossible to focus on the person you're talking to? It's just a wall of noise. But what's really weird is when this happens to people whose hearing tests come back, well, perfect. Their ears are totally healthy. So what gives? It's a real head scratcher. And this isn't just a small thing. For a lot of people, especially those with conditions like multiple sclerosis or MS, this is a huge deal. Get this, up to 40% of MS patients report this exact issue. They struggle with hearing in noisy places, but their audiograms, they come back totally normal. Their cochlea, that's kind of the ear's microphone, is working just fine. So, if the mic is working perfectly, then the problem can't be in the ear, right? It's gotta be somewhere further down the line. It's gotta be in the wiring. And that leads us straight to our prime suspect, a substance called myelin. Think of it as the brain's all-important electrical insulation. So what exactly is myelin? Well, it's basically this fatty stuff that wraps around our nerve fibers or axons. The best way to picture it is to think about the plastic coating on an electrical wire. It's doing the exact same job. And man, that insulation makes a huge difference. When an axon is wrapped in myelin, the electrical message is lightning fast, it's super reliable, and its timing is spot on. But you take that myelin away, the whole thing falls apart. The signal gets slow, it's unreliable, and the timing is just all over the place. The message basically gets scrambled. So that brings us to the big question the scientists in our source paper wanted to answer. What happens to our hearing? A sense that relies on signals that are incredibly fast and perfectly timed, when that critical insulation just isn't there. Okay, so to figure this out, the researchers had to get clever. They needed a way to isolate just the effect of myelin and nothing else. And they found the perfect way to do it. Meet the Long Evans shaker rat. Now, this little guy has a really specific genetic mutation. It means its brain and spinal cord can't produce myelin. This makes it the absolute perfect model for this experiment. It's a way to see, from day one, what a brain does when its wires have no insulation. So the scientists set up a two-part investigation. First, they went for the big picture. They recorded something called the auditory brain stem response, or ABR, which basically shows how the whole hearing system in the brain reacts to a simple sound. But then they zoomed way in, getting a microscopic view. They recorded the electrical signals at a single super important connection, a synapse, to see exactly how the message was being handed off. All right, let's get into the evidence. This is where we find the smoking gun. What the data showed was, without a doubt, a case of completely scrambled signals. And just look at this. The difference is night and day. On the left, that's the brain's response in a healthy rat. See those 5 clean, sharp peaks? That's a perfect, well-timed signal. Now look at the right. That's the signal from the rat without myelin. It's a mess, right? It's all distorted and smeared out. It's barely a signal at all. So what the scientists realized was that the message wasn't just late. Parts of it were completely missing. I mean, literally gone. 2 of those 5 peaks, they're called waves 2 and 3, were just absent, vanished. The brain wasn't even getting those parts of the message. Okay, the next clue points to a very specific problem. The researchers tested hearing at different pitches, and they found that the rats without myelin had a really hard time with high-frequency sounds. They had to crank up the volume way higher for the rats to even register them. And here's the kicker. This is the exact same kind of high-frequency hearing trouble that people with MS often report. The connection is undeniable. So that's the big picture view. But now let's zoom back in. What's happening at one single connection point? One synapse. When you really push it, when you make it fire super, super fast. Well, when they pushed that synapse to fire hundreds of times a second, the problem became painfully obvious. The signal just started dropping out. The nerve fiber with no insulation, it just couldn't keep up. It's exactly like when you're on a phone call with bad reception and the voice keeps cutting in and out. And you don't have to take my word for it. Let's look at what the scientists wrote in the paper itself. They said the recordings from the rats, get this, exhibited frequent AP failures. AP just stands for action potential, which is the nerve signal. So frequent failures. The connection was totally unreliable. That uninsulated nerve just could not fire over and over again at the speeds you need for hearing. So, we've seen all the evidence, the distorted signal, the missing pieces, the dropouts. What's the final verdict? What does it all point to? It all comes down to one single, incredibly important thing: timing. And really, if you remember one thing from this explainer, make it this. Myelin isn't just about making signals fast. It's about making their timing perfect, absolutely perfectly synchronized. There's a fancy term for it, temporal fidelity, but all it really means is that everything arrives exactly when it's supposed to.
So, why is perfect timing so ridiculously important for hearing? Well, think about how you know where a sound is coming from. Your brain figures it out by measuring the tiny, tiny difference, we're talking less than a millisecond, in when the sound hits your left ear versus your right ear. Now think about speech. It's not one sound, it's a crazy fast, complex stream of sounds. Without myelin, that precise timing just goes out the window. The signals arrive all sloppy and out of sync. It's like a signal jitter. And that jitter completely scrambles the information, making it impossible for your brain to do that hard work of separating one person's voice from all the other noise in a room.
And there you have it. The mystery is solved. The ear is doing its job, the microphone is on and working perfectly, but the message is getting garbled because the brain's own wiring, without its proper insulation, is scrambling the signal before it can ever be understood. So that leaves us with one last kind of mind-blowing thought. If perfect signal timing is this essential for hearing, just imagine all the other things your brain is doing right now. Thinking, moving, feeling. Where else is Myelin the quiet, unsung hero, working behind the scenes to make sure our entire experience of the world holds together?